Alright, just a part two to the other video where I don't know what happened to the second half of the video, but it's not there. So, I'll add this on again, and I'll try to have some kind of enthusiasm to describe it, but frankly, yeah, I've already did it. So maybe I'll draw it this time just so it's clear on what it is, and what I realized is that the lever doesn't really play a role in making it possible to couple the oscillator. So it's just the two mass and the one mass dangling on 88 inches of dangleables, string, so 88 inches. And the idea is you have a two mass and a one mass, and you initiate some kind of motion, and the motion basically just cycles through the two objects. Now in this case, okay, it's different than the other case, so depending on what kind of weight you put on, there's all these subtleties, because you can make it so it oscillates twice and then transfers to the other side, or it could be 3 times or 4 times. It seems that way anyway. So all I have is rubber bands here, okay, and connected to each other, and a lighter weight here. And so the lighter the weight, it seemed to work better with a lighter weight. And this is sort of doing the negotiating. And I guess I should point out that it doesn't dangle down in the middle. It dangles like this, pretty much. So the bias is in the opposite direction, sorry. Okay, the bias is in the direction of the half mass, the one mass versus the two mass. So it's basically, that's the experiment. So you oscillate this side, it oscillates to a maximum, and then the energy transfers to this side, and it oscillates to a maximum, and this is doing nothing. And it just keeps doing that hundreds of times. And that's the part that really surprises me, how little energy the system loses. And so from my perspective, this is sort of an ideal experiment to try to make very precise in terms of seeing where the energy is going, just because it is so lossless. And that's why I find it intriguing, because it's pretty simple. I mean, you kind of have to concede all the energy has to be over here, and and then all the energy is over here. It is. And this just reveals the problem with momentum and kinetic energy, that if you conserve the momentum, you have to make free kinetic energy. And if you conserve the kinetic energy, you have to make free momentum, or destroy momentum. And those aren't reconcilable choices. The only way you can reconcile them is to concede one of the formulas, one of the models can't be true. One of them doesn't mean anything, and one of them does. So I'll play the video, and it's not. Unfortunately, I recorded some of them, and the ones I didn't record were much better examples. But whatever, it'll have to do. So I just have a little Wi-Fi ear device here, so it's pretty light. Piece of plastic. So, and you can kind of see this one stops very well. Now, in other cases, the other one stops really well too, but not in this particular case. Okay, so the stopping of this one is a little elusive. You have to kind of project its stopping point. But obviously on this other side you can see it quite well. But the basic idea, as you can see, this little one is moving pretty close to twice the arc at its maximum that this one moves. And it looks pretty 2 to 1. Okay, somebody can make an argument, but it looks like this is going twice as fast as this is going, consistent with conservation of momentum, and not consistent with conservation of kinetic energy. And so this one's being pushed. So this is the maximum swing here, and then it'll start pushing this one. And this one's maximum swing is about there. And so it barely gets to the edge into here, where this one's going the full page, just about at its maximum, almost the full page. So, yeah, we'll see. I'll try to get some better video and make some kind of more precise frame rate calculations or whatnot, I suppose. But I'm just throwing it out there. It looks like momentum wins here, but whatever. Looks like is like. So need more than that. But I mean, it would be better if this experiment had been done somewhere in the history of physics by somebody doing it seriously. So again, I'm just going to raise the point. You people are all defending a physics that in 350 years, and it's even more than that for pendulums. I mean, pendulums have been around a long time. That no one's done this. No one's analyzed this precisely to see what actually physically really happens and how to modify it to make it do it more precisely or less precisely. There's no book on this. There's no textbook. Physics textbook doesn't say anything. It just says coupled oscillator, moves on. It has complex calculations, blah, 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 lots of math, but no real evidence. No, well, here, I'll show you. No, I show you. Nothing. And your people are all comfortable with that. You think that's good science. Good science is don't do the experiments, don't itemize, don't categorize, don't, pick at it and get as precise as possible. Just say it, just preach it. Don't bother proving it. So, I mean, it's bad on you people. So the other thing I just found, like I said, I already said it, but I mean, I just found it amazing how long this thing actually just keeps doing this, considering how trivial the amount of energy that went in is. It's not a huge amount of energy, and yet it goes on and on and on and on and on, pretty much doing the same thing. They get some precession in it, get some other things. So like I said, there are better examples where I have less noise in, and so there's less noise that filters out, so everything stays much more regular. But it does amaze me that it can just continue. Like even with just air resistance, you would think it would wind down a little faster than it does, and it just keeps going and going and going. So it's very conservative as an experiment, which is always a good thing. And so if you can get an experiment where you're losing very little, and you can get it to keep doing the same thing over and over, you should be able to get pretty good data from such an experiment. It's just tragic that it has to be done on my porch floor, and it can't be done better than that. That the science doesn't deserve better chronicling of the facts than what we get. Really is. I mean, the fact that no real physicist has redone not only the Eddington experiment, but they haven't even redone the Charolais experiments, the Clay experiments. We have Brozo redoing them. I mean, what is that? I mean, it's a junk experiment, don't get me wrong, but since it is so much a part of the history of physics, it really should be something analyzed by a physicist who actually explains to you, well, yeah, they are round objects, and if you're just denting the clay, you're not penetrating the clay, you're only denting it with a round object, yeah, that's not going to be linear. It's not going to tell you, it's going to treat things with different velocities differently. Alright, so I guess that's enough. 6 minutes. The camera battery went dead after 7 minutes and 43 seconds, so, but it is, I find it intriguing. It's just interesting. Just watching it is interesting, just because the way it duplicates other things like charge. You can imagine these being electrons repelling each other, and you can kind of see, how, that's how it would kind of work. Because it really looks like the two things are pushing on each other. But anyway, it's sort of redundant, but I'm still not, I'm still thinking on a way to work this out. And the other thing I'm thinking is to really go with the catapult idea, some sort of spring launcher. And it's just a matter of finding a way to do it without angular rotation problems or friction problems or some other bullshit, other problems of gravity, frankly. Just because of the arc problem. But again, at 88 inches, the arc is pretty low, so it shouldn't be too far from the truth to just measure how far they travel. And that should tell you pretty much their velocity. So I just have to work on how I want to design or engineer the experiment, but I think that's where I'm heading, because it gets rid of the problem with the lever, which is there's still losses in moving the lever. It's not a lossless system, and that's not good. So I have to find a way around that one. So, till the next time, and such, and so forth and whatnot. I think that's enough.